Afternoon. I'm Rob Parrish, and together with my co-authors Gian-Luca R Anselmetti, David Wierichs, and Christian Gogolin, I am pleased to share with you some of our results from our quantum number preserving gate fabrics paper, which is to appear in the New Journal of Physics. The basic problem that we're dealing with today goes back to an old problem in quantum computing. For instance, for a generic case of a qubit operator, how do you build up that complicated qubit operator or entangler in a way that powerfully explores the Hilbert space due to a number of internal parameters in that large gate as a product of lower gates? And for the case of generic rotations in the Hilbert space that do not have constraints on them, it has been known for a very long time that all you need to do is actually to build little entanglers, SO4 entanglers that are universal for the 2-qubit Hilbert space, and then construct a fabric of those smaller gates where you have alternating even and odd local pairings of the qubits, and this will saturate at a certain depth, which is exponential in the number of qubits that are involved. It will provide numerical universality, meaning that you can construct any rotation that you want there. While at intermediate depths, you have compelling properties as far as how much power this generic rotation has within it in exploring the full Hilbert space. But then when you go over to simulate fermions, i.e. the electrons in the electronic wave function of some molecule that you're trying to solve the Schrodinger equation for, you encounter the massive problem that fermions are not qubits, and that actually fermions are highly constrained by things like the total number of electrons. For instance, just for 2 spin orbitals under the Jordan-Wigner mapping, already there in that 4-dimensional 2-qubit Hilbert space, you see cases where you have no electrons, 1 electron, or 2 electrons. And generically, when you're trying to solve the Schrodinger equation for a system like that, you want to explore the Hilbert space with a constraint that you preserve the total number of electrons to be something like, say, the 1 block of this. And so the fabric on the previous slide will violate that symmetry and actually not be able to preserve that. And so what we're going to try to do today is to construct gate fabrics that are universal for fermions, and yet that preserve the locality of the circuit. In particular, noting that the fermions have actually 3 symmetry constraints to them, namely the number of alpha electrons, the number of beta electrons, and the very non-local spin squared operator that we must try to maintain there. The major result of our paper is that it is actually possible to do this, but you need a gate fabric of 4-qubit gates. You can't do it with 2 or 3-qubit gates, actually. What each of these Q gates do in this case is actually to solve essentially the full configuration interaction solution within these 4 qubits, these 2 spatial orbitals here. And then you alternate those back and forth in this fabric, and you get the universality property of the previous fabric, but in a way that's congruent with the symmetries that you had to maintain for the fermionic system. The Q gates, even there are many constructions of them, but one that's particularly simple is that you can build them out of pair exchange gates and orbital rotation gates that do operations like spatial orbital rotation or rotation of these seniority 0 diagonal double pairs that are very well known in classical electronic structure theory methods. In fact, these actually have a lot of overlap with other proposals, either things like Hartree-Fock or doubly occupied configuration interaction, or different rearrangements of other entangler circuit proposals such as KU-PCC-GSD or the generalized swap network extension thereof. And so very neat that we can actually build a gate fabric like this that preserves the linear locality and the simple structure of the gate fabric, and yet it has compelling properties as we make the gate fabric deeper as far as its ability to approximately solve the Schrodinger equation. For instance, for p-benzyne here with a 12-qubit 6-spatial orbital active space, this has a full configuration interaction exact solution that has 175 parameters to it. And as soon as we make the fabric deep enough that we cover that 175 parameters, we see the numerical onset of the exactness or universality property of our gate fabrics. We, of course, exactly saturate the constraints of number of alpha, number of beta, and spin squared. And then pragmatically, at lower depth, we rather quickly approach a level of accuracy that's acceptable, i.e. chemical accuracy for this system. So we certainly don't think that this one paper by itself is the end-all be-all of this, and it sits within a number of other really, really nice literature studies, but very compelling to be able to have such a low scaling, simple gate fabric that actually preserves these quantum numbers and allows us to powerfully explore the Hilbert space when simulating fermions.